We are done with the chapter of asymptotic notations where we discussed different types of asymptotic notations and the problems based on it. Now, from this lecture onwards, we are starting a new chapter where we will discuss how to find the time complexity and the space complexity of algorithms involving loops. In this lecture, we will first understand the time complexity in great details, and then through an example, we will understand how to analyze the time complexity of an algorithm involving loops. So let's get started with this lecture and let's see what are the topics. The first topic of this lecture is Priori versus Posteriori analysis recap. We will first get the quick recap of priori and posteriori analysis, and then we will understand CPU computations and main memory space. We will understand these two terms in great depth, and then we will understand the time complexity, and finally through an example we will understand how to analyze an algorithm, and that too an algorithm which involves loops. So let's get started and let's get the quick recap of the priori versus posteriori analysis. We know the difference between priori and posteriori analysis from our previous chapters. Let's get the quick recap of priori and posteriori analysis. In case of priori analysis, we estimate time and memory space required by an algorithm before executing it on the system. But in case of posteriori analysis, we calculate time and memory space required by an algorithm after executing it on the system. Here, in case of priori analysis, we estimate time and memory space. This means we do not calculate the actual time and memory space required by an algorithm, and we estimate time and memory space before executing our algorithm on the system. So before executing the algorithm, we estimate time and memory space it takes. In case of posteriori analysis, we calculate the actual time and memory space required by an algorithm after executing it on the system. So posteriori analysis depends upon the system. Priori analysis does not depend upon the system because we are analyzing the time and memory space required by an algorithm before executing it on the system in case of priori analysis. Our focus is on priori analysis because priori analysis is the easiest and it is the most practical analysis. So keeping this in mind, we will use priori analysis to analyze our algorithms. Now, how do we estimate time and memory space is the main question. The estimation of time is same as the estimation of total number of CPU computations an algorithm takes, and estimation of memory space means estimation of main memory space. We will understand how do we estimate main memory space later, but in this lecture, we will understand how to estimate time, or in other words, how to estimate the total number of CPU computations an algorithm needs to execute. Now, what is the meaning of CPU computations? Let's understand the meaning of CPU computations and main memory space first. After this, we will learn how to analyze an algorithm, or in other words, how to estimate time and memory space required by an algorithm. So now, we will understand the meaning of CPU computations and main memory space. So what is the meaning of CPU computation? A CPU computation refers to a task performed by the CPU or instruction executed by the CPU. So CPU computation refers to a task which is performed by the CPU at any point of time, or it refers to an instruction executed by the CPU in simpler terms. So the meaning of CPU computation is an instruction executed by the CPU. Now, what is the meaning of main memory space? Main memory space is used to temporarily store data and instructions that CPU needs for quick access during program execution. One thing is clear, that our focus is on CPU or central processing unit. Whenever a CPU performs a task, we call it a CPU computation, or we can say whenever an instruction is executed by the CPU, we call it a CPU computation. And we are focusing on the main memory space because main memory or random access memory, which we also call RAM, is required by the CPU for quick access of the data and instructions stored in it. Main memory space is of concern to us, and we are also concerned with the total number of CPU computations required by an algorithm. So these are the two terms which I hope are completely clear to you. The meaning of CPU computation is an instruction executed by the CPU, and main memory space is the memory space required by the CPU for quick access of data and instructions during program execution. Now, as we have understood the meaning of CPU computations and main memory space, we are in the state to understand the time complexity. So, what is time complexity? Time complexity refers to the estimation of total CPU computations required to execute an algorithm. We just understood the meaning of CPU computations. We are not bothering about main memory space at this moment. Later we will understand how to estimate main memory space. But right now our focus is to understand the time complexity. And time complexity is the estimation of total CPU computations required to execute an algorithm. Now the main question is, how do we estimate total CPU computations? We now know time complexity of an algorithm is equal to total number of CPU computations. But the question is, how do we know the total number of CPU computations of an algorithm? We can calculate the total number of CPU computations by using the method which we call the frequency count method. According to this method, we calculate the sum of frequency count of each instruction of an algorithm. So, frequency count method is the method in which we calculate the sum of frequency count of each instruction of an algorithm. So, total number of CPU computations is equal to the sum of frequency count of each instruction of an algorithm. Now, what is the meaning of frequency count? Frequency count refers to the number of times an instruction is executed. So, in order to calculate the time complexity of an algorithm, we calculate the sum of frequency count of each instruction of an algorithm, and frequency count refers to the number of times an instruction is executed. So by seeing an algorithm, you can calculate its time complexity. And now we will understand how to do this. So now we are going to take a simple example algorithm, and through that algorithm we will understand how to calculate the time complexity, and that too using the frequency count method. So now let's move to the next topic, where we will consider a simple example algorithm to understand the time complexity properly. Here is the example algorithm. Here I have written the algorithm in C-like syntax because C-like syntax is simpler to understand, and many students might already know C programming language. So it is my assumption that you are familiar with at least one programming language, if not C. If you know C programming language, then it is great. But if you don't know C programming language, you can still follow along. there is no issue. This algorithm is written in C-like syntax, and I've mentioned algo here to indicate that this is not a C program. This is an algorithm. This algorithm is non-executable. This algorithm is written for us to understand how to analyze the time complexity. So now we are going to analyze the time complexity of this algorithm using the formula which we just saw. We are going to use the frequency count method to calculate the time complexity of this algorithm. So we will do the priori analysis of this algorithm. This means we will estimate the time complexity of this algorithm through the frequency count method. Now let's proceed and let's do this. The job of this algorithm is to calculate the sum of n elements of the list A. So n represents number of elements and A represents list of n elements. Here in this algorithm, the first instruction is sum equal to 0. This instruction tells CPU to assign 0 to variable sum. Here, only one operation is performed, hence this is just a single instruction. And this instruction is executed only once. So the frequency count of this instruction is 1. Now why is that the case? We know the meaning of frequency count. Frequency count refers to the number of times an instruction is executed. This instruction is executed once. Here we have just one assignment. That's it, only one operation. And it is executed only once. Therefore, the frequency count of this instruction is 1. And let's assume that one instruction takes 1 unit of time. Therefore, this instruction takes 1 unit of time. Now, if we want to know the time complexity of this algorithm, we need to calculate the sum of frequency count of each instruction in this algorithm. So let's put 1 here. Here we will calculate the sum of frequency count of each instruction. The frequency count of this instruction is 1, and this is the reason why I have written 1 here. Now what is the next instruction? This is the for loop, and I hope you already know the meaning of for loop. For loop allows us to execute instructions a certain number of times. This loop will allow us to execute this instruction, which is part of the for loop, a certain number of times. In this for loop, we have this instruction I equal to 1. This is an assignment instruction, and this instruction will be executed only once because this represents the initialization of I. So, clearly, the frequency count of I equal to 1 is 1, and therefore the time it takes is 1 unit, and hence 1 can be added in this sum. Now what's the next instruction? The next instruction is I less than or equal to n. What can we say about this instruction? What is the frequency count of this instruction? I want you to pause this video and I want you to think about this. What is the frequency count of this instruction? So pause the video now. I hope you're done. Okay. So what's the frequency count of this instruction? The frequency count of this instruction is n plus 1, and hence it will take n plus 1 units of time. Now why is this the case? You might have given the answer as n, and you are quite close, but n is not the correct answer. N plus 1 is the correct answer. Why? Let's find out. We know here we are checking a condition. We are checking is I less than or equal to n. If it is the case that I is less than or equal to n, then this statement sum equal to sum plus ai will be executed. Then I is incremented and the condition is checked once again. So we know the initial value of I is 1. 1 is compared with n. This is the first condition checking. First we are checking, is 1 less than or equal to n? If true, we will get inside and execute the statement. Then I is incremented, I becomes 2. Then we will check this condition once again. Is 2 less than or equal to n? This is the second condition check. Then we will go inside, execute this statement. I is again incremented, it becomes 3. Then 3 is compared with n. This is the third time the condition is checked. And this will continue, and then we will compare n with n. Eventually I becomes n, and we will compare n with n. But we know n is equal to n, it is not less than n. Still the condition is true, and hence the statement inside the for loop, that is sum equal to sum plus ai, will be executed. And I is incremented by 1. We know I is n, and n plus plus is equal to n plus 1. So the next condition check is n plus 1 less than or equal to n. Can we say n plus 1 is less than or equal to n? No, right? N plus 1 is not less than or equal to n. It is greater than n. Therefore, at this point, this condition becomes false. Hence, we will go outside this loop. We are done with this loop at this point. How many times this instruction is executed? A total of n plus 1 times. Therefore, there are n plus 1 comparisons. And hence we can say the frequency count of this instruction is n plus 1. And this is the reason why this instruction will take n plus 1 units of time. So now we can add n plus 1 here. I hope this point is clear. Now what can we say about this instruction I++? How many times do you think this instruction will execute? Let's try to understand this now. This instruction will execute based on this condition. If this condition is satisfied, this means if this condition is true, then this instruction will execute. If this condition is false, then this instruction will not execute. Why am I saying this? Let's now try to understand this. The initial value of I is 1. Let's say 1 is less than n. This condition is true. If this condition is true, we will go inside the for loop and execute this statement. After execution of this statement, I++ will execute. So it is clear, when this condition is satisfied, I++ will execute. But what when this condition becomes false? If this condition is false, then this statement sum equal to sum plus ai will not execute. And hence, this instruction will also not execute because I++ can only execute after execution of this statement. So one thing is clear, that when this condition is true, I++ will execute. If this condition is false, then I++ will not execute. Now let's use this idea to understand how many times this instruction will execute. The initial value of I is 1 and I'm assuming 1 is less than n. Therefore, the condition is true. After execution of this statement, I is incremented by 1. This means I++ is executed for I equal to 1. After execution of this instruction, I becomes 2. After I becomes 2, this condition will again checked. Let's say 2 is also less than n. The condition is once again satisfied. As this condition is satisfied, I++ will definitely execute. So, for I equal to 2 also, this instruction will execute. What about I equal to 3? Let's say for I equal to 3 also this condition is true. Then it is surely the case that I++ will execute, and hence for I equal to 3 also I++ will execute. Similarly for I equal to 4 also this instruction will execute. Again assuming the same thing, that 4 is less than n. Now let's say this process continues up to I equal to n. When I becomes n, then n is compared with n. As this condition is satisfied, I++ will again execute. Therefore, for I equal to 1 to n, this instruction will definitely execute. After I equal to n, this instruction will execute and hence I becomes n plus 1. We know that this condition will be checked once again for I equal to n plus 1. But this time this condition is not satisfied because n plus 1 is neither less than n nor it is equal to n. As we know the condition is not satisfied, therefore I++ will not execute this time. So for I equal to n plus 1, this instruction will not execute. Only for I equal to 1 up to n, this instruction will execute. And this clearly shows that I++ will execute n times, not n plus 1 times. Hence, the frequency count of this instruction is n, and the amount of time this instruction will take is n units. So now we got to know that this instruction will take n units of time. So now we can add n here for this instruction. Now what about this statement, sum equal to sum plus ai? This is one statement, but in this statement we have a total of 2 instructions. Here we are performing the addition operation and we are also assigning the result of sum plus ai to sum. So there are a total of 2 instructions. Now how many times do you think this statement will execute? This entire statement will execute n times because of the same reason which we saw in case of I++. The execution of this statement also depends upon this condition. Hence, when this condition is true, then this statement will execute. When this condition is false, then this statement will not execute. So it is clear the number of times this statement will execute is also n. But here we have a total of 2 instructions. Therefore, the total time required to execute this statement is 2n units. The frequency count of the statement is 2n. So now we can add 2n here as well. Now what can we say about this statement, return sum? This is just one instruction and hence it will take 1 unit of time. So we can add 1 here for this instruction. Now here we can calculate the total frequency count of this algorithm. This is equal to 4n plus 4 because 2n plus n is equal to 4n. 1 plus 1 plus 1 plus 1 is equal to 4. So we got 4n plus 4. As 4n is the dominating term, therefore big O of n is the time complexity of this algorithm. We can use different notations here to represent the time complexity, but I am using the big O notation, which is also correct. So the time required to solve this algorithm is big O of n, which is the linear time. As the size of the input grows, the time required to solve this algorithm grows linearly. It is big O of n. Now we know what is the time complexity of this algorithm, and we got to know this by knowing the frequency count of each instruction of the algorithm. In this way, we can calculate the time complexity of any algorithm. So I hope the idea is completely clear. With this, we are done with all the topics of this lecture and hence we are done with this lecture. Okay friends, this is it for now. Thank you for watching this presentation. I will see you in the next one.